Okay, so this is our first triple integral. So really, there's nothing, just doing an iterated integral, there's nothing difficult about it. I mean, well, I shouldn't say that. I mean, it's straightforward. It's just like a double integral, except there's three of them. So the bounds are x goes from -1 to 5, y goes from 0 to 2, and z goes from 0 to 7. So I'm going to have the outside be the z integral, z equals 0 to 7. Then the y integral, y goes from 0 to 2. And then the x integral, x goes from -1 to 5. And then you integrate x z minus y cubed, and then dx dy dz. Okay. Okay, and according to Wolfram Alpha, you can see this answer is 420. Okay, now, the Wolfram Alpha thing was kind of a joke. You have to be able to do this type of integral, but it's tedious, and it's just integrating polynomials, and I think we're all good at doing that now. Okay, so the main thing for this, the only new thing about this problem is it is an iterated integral, but instead of there being two integrals, there's three of them. And in general, this is just how iterated integrals work. You do the inside integral first and just work to the outside. Okay, now we're getting into a more difficult integral because it's going to be a region. The region is more complicated. The region we did up here is just a rectangular prism. Okay, the region that we have down here is more complicated. So the first thing that I think you should do, well, I guess read the problem. So it's bounded by y equals x squared, x equals y squared, z equals 0, and z is equal to 5x plus 5y. Okay, so I think it's a good idea to try to find a bottom of the shape and the top of the shape, or something like that. So notice that z equals 0 is going to start from z equals 0 and go up to this plane z is equal to 5x plus 5y. So, and it's going to be over this region y is equal to x squared and x is equal to y squared. So this is really the way that I like to think about this. Try to find something that's like a top and something that's a bottom. Okay, now the top and bottom could be oriented left and right, but that's just sort of the way that I think. So here the obvious bottom I think is z is equal to 0, and the top is z is equal to 5x plus 5y. Okay, so let's think about what this is going to look like in the xy plane. So if I graph these two functions, these two curves, y equals x squared and x equals y squared, in the xy plane, you get something like this. Oh. Okay, y equals x squared looks like this. Actually, I want to do this in red. Y equals x squared looks like this. And x equals y squared, that's the same as y is equal to the square root of x. It looks like this. Okay, this is the region that we're going to be, this is like, if you were to project this region onto the xy plane, this is the region. Okay, now, what I'm saying is that for every fixed value of x and y in this shape right here, for every value of x and y in this shape right here, z is going to go from 0 to 5x plus 5y. So the innermost integral will be the z integral. Z will go from 0 to 5x plus 5y. Okay, next we'll say we'll do the y integral. Okay, now for every fixed value of for every fixed value of x, y, we're going to integrate from this point to this point, from the bottom curve to the top curve, from the y equals x squared to the x equals y squared. Okay, and these are supposed to be straight up and down. So this is y is going to go, okay, so this line is y is equal to x squared. So it's going to go from y is equal to x squared up to the curve x is equal to y squared. In other words, y is equal to the square root of x. And then x is going to go from this point here to this point here. Well, the x coordinate of where these two curves meet is 1 because it's where x squared is equal to the square root of x, and we're in the x positive part. So this is going to be 1. And then we have the function that we're integrating, which is 4x y dz dy dx. And this this right here is an x squared. Let me make that look a little bit better. And this is equal to 15 over 7. Okay, so again, the first thing was try to get an idea of what this region looks like. Just because of the way the region is given, it makes sense to integrate with the z integral on the inside because we're given these curves y equals x squared and x is equal to y squared. So it seems like we should have the xy integrals be on the outside and the z integrals be on the inside. And as you do more of these problems, you'll get a better feel for what is the best choice to make.